So I like to thank Professor Yongnam Lee for giving me the opportunity to give lectures in this school. So let's explain. Let's write down the plan. So in the first lecture, I will talk about the MMP, and I will explain what MMP is. Okay, in dimension 2. And tomorrow, lecture 2 and 3, I will talk about the MMP in dimension greater than or equal to 3. So this is a story developed until around 1900. And the story in dimension 3 is around 1980s. Okay, so to go from dimension 2 to 3, it took almost 8 years. So there is a very significant difference from between 2 and 3 or higher. Okay, so and some of the contents in my first lectures overlap with Dongsun's lectures. So okay, so let's start with a surface S, which is smooth, projective surface over C. Okay. So in birational geometry, there is a fundamental question. Find a good model in the equivalence class of S. Okay. Well, of course, we need to know what this good means. Okay, so it can mean so it's already smooth. So let's say this one is possibly singular. Okay. So this good may mean smooth. Okay. So first you want to find the smooth model which is birationally equivalent to the given surface S. Okay. So this is already solved by Hironaka. This is very well known. Okay. And in the minimal model program, this good means minimal. Minimal. In the following sense. So if in the sense that if S from so if X is the minimal element to X birational morphism, then phi is isomorphism. Okay. So the goal of the minimal model program is to find such element. So if you start, so you want to find the minimal model, which is denoted here by X min. And if there is a birational morphism to another model, then this map must be an isomorphism. Okay. And this was solved in 1900s around 1900 by Algebric Italian geometers. So today I will talk about how they did this in detail. Okay.
The resolution is maybe not greater, even in surfaces like that.
Yes. So, okay. So, in general dimension, in higher dimensions. Okay. Okay. So let's anyway. Yeah. Okay. So let's start the story. But the first part is very elementary, and some of them I took from Hashun's book. So let's use S here. Okay, S up. Okay. So let's start from the -1 curves. It is well known that by blowing up a point in S, we get a -1 curve. I think this is too well known by now. Okay? And by -1 curve, we mean C is isomorphic to P1 and the self-intersection number is -1. Okay. And let's repeat the theorem of Castelnuovo. If surface already has a -1 curve, it can be contracted. Okay? If C is a -1 curve on S, then there exists a bidirectional morphism such that S IC is a point. Let's say the point P, and S is a blow up of P. Blow up of S prime of P. Okay. So the only way to get -1 curve is blowing up a surface at some point. So -1 curve can be contracted. So we obtain the statement. Okay. So basically, in higher dimensions, we want to generalize this statement into the higher dimensional cases. Okay. Let's say theorem 1 and theorem 2. So this is already stated in Dongson's every smooth surface is birational to a surface, a smooth surface with no minus 1 curves. And this is also well known. The proof is very easy. Just apply theorem 1 finitely many times. Because every time you apply theorem 1, the Picard number drops by 1. And the Picard number is finite and greater than or equal to 1. So you can only apply theorem 1 finitely many times. Okay? So this is very well known. And I will denote such surface by minimal surface. Okay? So I will distinguish the minimal surface and the minimal model. So I will not say minimal model in dimension 2. Actually, if you look up in some literature, this is also called classically minimal model. A classical minimal model in some literature. And here is a remark. A surface may contain infinity many minus 1 curves. So there are many examples, but the most famous one is the blow up of P2 at very general 9 points. Okay, so on such surface, you have infinitely many minus 1 curves. Okay, so it doesn't mean you can apply. So here, this means even though you have infinitely many minus 1 curves, you don't apply theorem 1 infinitely many times. Okay, so here the Picard number is 10. And
So first theorem, the S prime is a smooth.
yes, smooth. Smooth. Okay. And the second remark is that minimal surface is not unique. And the example is this. So you blow up P2 at 2 points. P2 at 2 points. P1 and P2. So here you have P1 and P2. So if you blow up at these 2 points, you get 2 minus 1 curves, E1 and E2. And there is also one more minus 1 curve. So so E1, E2 are minus 1 curves over P1 and P2. And actually there is one more minus 1 curve, E3 proper transform of the line through P1 and P2. So you take the proper transform of the line through P1 and P2. Okay? And you can check that this is also minus 1 curve. It's easy to check. So now you can blow up E2 and E2 to get P2. So contract, if you contract E1 and E2, then you get P2. You recover the original surface. But if you blow down E3, then you get P1 cross P1. Okay? So according to this definition, these two are minus minimal surfaces. And last remark is, I just took this from Hashon's book, a minimal surface. Surface is minimal. That means if S, so if S is a minimal surface, in this sense, and S prime is a birational morphism with smooth S prime, then the map is an isomorphism. Okay. So I erased, but this smooth surface is minimal in the original sense. Here, it's here. Okay. So now, we want to define what minimal model is officially. Okay. Because so later on we want to generalize this Castelnuovo's theorem in higher dimensions. So it's not obvious how to generalize -1 curves. So it's not easy to generalize -1 curves in dimension greater than or equal to 3. And the other problem with this definition is this. Somehow we want the minimal surface to be unique. So we want minimal surface to be unique. Okay. So we came up with this definition. So S is a minimal model. Let's say a surface. S is a minimal model. If S is smooth and the canonical divisor is NF. Okay. So we will see that with this definition, the minimal model will be unique, and using this notion, it's easy to generalize the notion of these contraction theorems. So let's compare these two definitions. So this is also a very obvious remark, but a -1 curve. C is K negative. Okay. This is very easy to check using the adjunction, the genus formula. Okay. So but the converse is of course not true. But the converse is not true. That means, in other words, minimal surface may not be a minimal model. Okay. Actually, we've seen the example here. So these surfaces are minimal surface. These are minimal surfaces, but they are not minimal models. Actually, these are, yeah. So in these examples, minus k will be always minus k is ample. So with respect to any curve C, so this will be positive. So k will be never NF. So what does this tell you? So this also says that there are k negative curves that are not -1 curves. So we want to somehow classify the k negative curves. But to do so, Dongson already defined N1 and Kleiman-Morick ones. M-E. Yes. And so instead of classifying k negative curves, we want to classify k negative extremal rays. Okay. Yeah. So we want to classify k negative extremal rays. So here is theorem 3. Actually, this is the contraction theorem in the surface version, without using difficult theorems. So we have N1 and the Kleiman-Morricone. So let R be an extremal rate. Which is negative. So I'll just say K negative extremal. K negative. Then R is spanned by a rational curve. C and there is associated morphism high, which contracts C as follows. So we have three cases. And here is a little remark. If C is a -1 curve, then you can check the CK is -1. Okay, so here is a little remark and 1. CK, so we have three cases. CK is -1, CK is, sorry, CK is -2, CK is -3. So we only have these three cases. So first case, this is actually just the blow down of -1 curves. The pi is brought down of C. Okay. In this case, C is a -1 curve. And CK, when CK is -2, then C is -1 curve. And C is a fiber of a P1 bundle. S to another, this is a smooth curve. And in this case, C is just a line in S, but in this case, S will be isomorphic to P2. And in this case, pi will be just the structure morphism with C, so S to spec C. Okay. So if we have an E, the Morricone, It looks like this. And you intersect with the hyperplane defined by k equals 0. And this is the negative side, and this is positive side. And you have extrema rays, k negative extrema rays. Okay. And such ray R is spanned by a rational curve C, which is one of these, and for each R, you have the associated contraction. Okay. So in any case, K negative extrema ray R can be contracted. Okay. So, and actually this is the statement we will get in the high dimensional case too. So in the original definition of a minimal surface, you only need to contract the -1 curves. But with this definition, you need to contract all the k negative rays, k negative extrema rays. So actually, I had the same flow chart in the of the surface MMP chart of MMP in dimension 2. So I will just let's review. Okay, so let's say S is smooth surface, smooth projective surface. Okay. And you ask whether K is NF or not. And if yes, you get a minimal model. Okay? S is a minimal model. And if not, you look for K negative extrema rays. There exists K negative extrema ray R with the associated contraction S to some, so let's write S prime. Because here S prime may not be a surface. Okay, so you contract the negative extrema ray. So if I is birational, if yes, you go to the beginning. If not, you obtain modifiable space. Okay. And this was defined in Dr. Takuzo's talk. Okay. So as Dongson explained, you can only run this cycle on finitely many times, because after each cycle the Picard number drops by 1. Okay, so it's very well known. Okay. So actually, so MMP means this whole process. So simply you can view this as MMP S. So as the output, you get minimal model, or you get more modifiable space. Okay. Let's just write from S to some X modifiable space. Okay. So how do you know which one you get after you run the MMP? So this is already remarked in Dr. Takuzo's talk, but if the quadrilateral dimension S is non-negative, you get minimal model. And if the quadrilateral dimension is negative, then you get modifiable space. Okay. Okay. And this, with this definition, the minimal model also satisfies the minimal condition. So, actually, we have something, some stronger statement, a minimal model in dimension 2 is unique. As it was already explained, in higher dimensions, the minimal model is not unique. It's only unique up to codimension 1. But in dimension 2, the minimal model is unique. Actually, I didn't plan to explain the relation between the minimal models in higher dimensions, but I will explain how they are related. They are related by something called the flops. Okay, so I will talk about this tomorrow. And also, furthermore, a minimal model is also minimal. Okay. This follows from the theorem due to by a theorem in Harshon's book. Okay. So if any bilateral map from smooth, not Harshon's, Matsuki's book. Any bilateral map from a smooth surface T to a minimal model is a morphism. Okay. So using this theorem, you can prove the uniqueness and this minimality condition. Okay. Okay. And lastly, this was also mentioned in Dongsun's lecture, but I will also say something about the abundance conjecture. Now, abundance theorem in dimension 2. In dimension 2. Okay. So let's say S is a minimal model in dimension 2. Okay. So it's smooth and Ks is net in this case. And so Neff's condition is what? Neff means Ks is not negative. So there may be some curves. Let's see, C. So there may be some curves C such that the intersection is 0. So we want to contract such curves. Okay. So this theorem says that. So in this case, MKS is base point 3. Point 3 for large M, for sufficiently divisible and large M. Sufficiently large M. Okay. So using this linear system, we can define a morphism from S to some X. Okay. And actually, what you get in the image is called the canonical surface. Okay. And the property of this morphism is exactly this one. So so this is the statement of the theorem, but this says that this implies that there exists a morphism from S to some canonical model, such that this was already mentioned, but the Kodaira dimension of S is equal to the canonical model, and K S, the canonical divisor of the canonical model is ample, and pi C is a point if and only if KSC is 0. So this is the map precisely which contracts the curves whose intersection is 0 with respect to the canonical divisor. So tomorrow I will state everything in higher dimensions, and I will try to tell you which one is true and which one is still open. And today I didn't talk about the singularities. All the surfaces are singular except this one. So up to this point, everything was smooth, but after you apply this abundance theorem, then this canonical model will be no longer smooth. So actually, because Dongson already talked about some of my stuffs, and I skipped. So it's not. We can talk about a little bit about what I was going to talk tomorrow. Okay. So we want to realize everything in higher dimensions. So as I said, there is a major difference. So this is the beginning of lecture 2. So goal is still to find the minimal model. Okay? So given a variety X, find a birational map to a minimal model. So here I didn't define the minimal model yet in higher dimensions, but it's almost the same. So, but except that we allow singularities. Okay, so I will define later on. Okay, so this is first. And the second goal is to find the types of singularities. These we can allow. To run MMP. Okay. Actually, we can also find the largest types of So to start with, so from now on, the X will be a normal projective variety defined over C, and the dimension is greater than or equal to 2. Okay. And this was also briefly talked about, but to check whether a divisor is NF or not, we need Q-Cartier property. This was also defined in the previous talk, but this means any value divisor is Q-Cartier. Yeah. Oh no. So yeah. So Q fact definition. X is Q factorial. If any value divisor is Q-Cartier. So this means if you have a divisor D for any value divisor D, there exists M. Such that MD is Cartier. And Q Gorenstein means X is, so we will not use this, but Q Gorenstein. If Kx is Q Cartier. So Q factorial is good, not only because we have intersection numbers, we can also pull back divisors. So another advantage is that we can define pullbacks of divisors. Okay? So let's say D is a value divisor, and you want to pull back. So you multiply some integer, and this becomes a Cartier, and now you can pull back. Okay? So that means we define the pullback of D as so we can define pullbacks of any value divisors. Oh, and of course there is an example of a variety which is which is not Q factorial. So this is also in Hashon's book. And so let's say X is a quadric cone in P3 locally defined by xy minus c squared. Okay. Then you can check that L, which is defined by x equals z equals 0, is not Cartier, but 2L is Cartier. So this is an example of a divisor which is Q Cartier, but not Cartier. Sorry, and I will define the singularity you are going to study tomorrow, and I will finish. So from now on, X will be Q factorial, and normal and projective. Okay, and definition. Let's say let f from y to x be a resolution of singularities. And the exceptional divisors. is simple normal crossing and the support. Okay, so there are divisors which is contracted on X, and we collect all of them, and they have simple normal crossings. And so with this resolution, we can write ky kx plus ai ei. And ai is called the discrepancy. Of E. And in the literature, it's sometimes denoted by EI. And we say X is terminal if AI is positive for all I, canonical if AI is non-negative for any I, log terminal. Now, if AI is greater than -1, it's a log canonical. If AI is greater than or equal to -1 for any I. So in dimension 2 case, this locally this one corresponds to smooth. And each has descriptions. This is locally defined by, so in dimension 2 case. C2 over some finite subgroup. Finite subgroup of SL2. And this third one is the C1, C2 ordered by a finite subgroup of GL2. So this is nothing but smooth in dimension 2 case. And this also has some description, but it's more complicated than this. Okay. So tomorrow, so actually for this case, so we will allow log terminal singularities. So we will always assume log terminal singularities. Okay. Okay. Then all the results, including contraction theorems and all the important results hold, even with these bad singularities. Okay, so anyway, tomorrow I will recall the definition of singularities again. So if you don't study minimal model program, it's really easy to forget the definitions. Okay. So I will stop here and I will continue tomorrow.